The basic point I want to make is that I think we need to, it's very valuable to take more seriously the subject. We talk a lot about the object, and we talk a lot about the environment, but there is also degrees of freedom in our universe which can be self-aware. I don't believe that there's any secret sauce to consciousness, but clearly there's something special going on in your brain that makes you aware of the rest. And if you look carefully at the quantum mechanics of that, I think that teaches us a number of interesting lessons. So that's the basic theme I want to come back to here a number of times in the talk. But first, just as a warm-up, let's talk a little bit about classic decoherence calculation that I recently finished with a student, Dan Roberts, at MIT. And then we'll talk more about the subject and decoherence and observation and how that leads to some interesting generalization about the second law of thermodynamics. And then I want to talk a little bit about the fact that Wojtek's wave function is in a superposition of astrophysics and quantum mechanics, just like mine, coincidentally. So I've been inspired by you in many ways. And I want to talk about that when you put together these two branches and try to interfere them, they actually have some very interesting things to say about each other. But let's start off with the first part here, just the classic application of decoherence, interaction between the object of study and the environment. The inspiration for this is a paper that Wojtek wrote a very long time ago with James Anglin, whom I got to meet when you invited me to Los Alamos that time, where they looked at how the electromagnetic field is decohered. And the basic conclusions that they found were, sure enough, first of all, the environment explains why the electromagnetic field appears classical on the particular basis that we feel it tends to be classical. And they also they introduced this very nice idea of a quantum halo. Namely, the idea that you can describe in the space of all configurations that the electric field can have. It's a very highly dimensional space, of course. There's a point there, which is the classical state of it, which evolves around. Then there's a little ball, a little quantum fuzz around that, which evolves around. And you can, by decoherence, estimate the size of that halo. So in other words, how different the two electric fields have to be for them to be really distinguishable. So you can't get any coherent interference effects between them. So we did a calculation where we took the same idea and applied it to the space-time metric. I've been interested in this for a long time, since space is much of what I study, and the space around us here is one of the most classical things that we know of. But of course, there's nothing preventing, in principle, us having the metric being in a superposition of many different states. So the distance between me and Wojtek is a superposition of 5 meters and 6 meters and 7 meters. We don't seem to perceive that, particularly, at least while sober. So there must be very strong decoherence happening. Something in the environment is learning about this. So let me just very briefly tell you what we did. The most powerful effect that we found is the effect of a lot of particles just flying through space all the time. And the cosmic background neutrinos turn out to be the winners, as I'll explain in a little bit. They're everywhere. You can't shield against them. These 2 Kelvin neutrinos left over from the Big Bang, they go through everything. There's a very high number density of them. How do the neutrinos find out about what's going on in space-time? Well, think about a wave packet here. You can think of this as a neutrino coming, or a photon, whatever. It flies through some region of space. Let's suppose that in this particular region of space, the metric is in a superposition of just 2 different states, to keep it very simple to start with. Either there's nothing there, so it's Minkowski space, or there's some blob of matter, so that we have a Newtonian potential which is non-zero. Okay? So we'll think of, when I think of a superposition of 2 metrics, you can think equivalently of a superposition of 2 different mass distributions that are sourcing it, if you want. What's going to happen? Well, there's going to be a Shapiro time delay. Very well-known effect that the photon will take longer to go through a region strong gravitational field. So when it comes out, if the metric is in a superposition of two states, when you look afterwards, the photon or the neutrino is in the superposition of being here and being somewhere else. So clearly there's information encoded in the particle afterwards about the state of the metric. The photon or the particle has observed one aspect of the metric. It hasn't observed everything about it. What has it observed exactly? Well, the Shapiro time delay is simply the integral of the metric, of the Newtonian potential specifically, along the flight path of the particle. Okay? If you go back to the Old Testament, decoherence, say, Zurich, and so on, that reduced density matrix for the thing you're interested in this case, the gravitational potential, just gets multiplied by some decoherence factor, which is just the inner product of, in this case, the two different particle states. So if these get separated by much more than the width of the wave packet, then the particle can tell the difference. Otherwise, it cannot tell. What is this decoherence factor? Well, we worked it out quite generally with a Klein-Gordon equation, but the bottom line is you get this exponential suppression where in the exponential you have the Shapiro time delay divided by the width of the wave packet. Basically, this is the speed of light equals 1 here. Now, if you also get gravitational lensing, where the particle also gets bent sideways if there are gradients in the metric. It turns out that the Shapiro time delay generally beats out the lensing as the most powerful effect. Quick question there?
What's going to set that wave packet width in a second?
Oh, this is just a general calculation so far where you can, I'm just saying, if you pick a particular, create any particular wave packet you want, send it through, figure out what happens. What I'm going to do, you're psychic. You're predicting what I'm going to do on the next slide, which is now put in lots of different particles that actually exist and see what happens. In the real universe, you have these neutrinos flying through not just along one line of sight, but along all parallel line of sights, and in fact in all possible different directions as well. So the information about all different line integrals of this function get measured, right? And this is exactly like what happens sometimes in the hospital. So Bill Unruh couldn't come because he had to have kidney stones taken out yesterday. I don't know if he had a CAT scan, but the idea there is precisely this. You send X-rays through somebody, and each X-ray flight path probes the density along a line, but it's well known that if you get it through all different lines, you can recover exactly what's inside, down to the wavelength of the particles and other things. So we did the analogous calculation and inverted the radon transform to ask how much do these neutrinos actually learn about space-time, and we found this. In the end of doing all the math, this is a very simple formula where the decoherence factor is a function of the delta phi here, the fluctuation in the metric, is given by this very simple integral. Let me say it a little bit in words how I think about it. So this formula basically defines the Zurich-Voitek's quantum halo. It tells you this space-time here, we have a classical background metric with a quantum halo around it. So there are some very small fluctuations you can have around it, which will be quantum, but not classical. But if the metric differs more than that, you're outside the quantum halo, you get decoherence. How big is the quantum halo? Well, it's very bounded. It's a ball. It's in fact a sphere in a very high dimensional space, because you can see it only depends on the sum of the squares of all these components. In Fourier space, interestingly, not real space, that happened from the radon transform. What's happening is that all Fourier modes of the metric are being decohered up to a maximum Fourier mode, which is set by the wavelength of the neutrino, of the particle. Basically, the particle doesn't see fluctuations that are much shorter than its wavelength. It's sort of intuitive. And then there's some other factors here to do with how long, with the number density of neutrinos and a few other things. When you put this in, put it all together, you find, as I've plotted here, is the quantum halo by just asking how small fluctuations in the amplitude of the and metric fluctuations can you detect versus the length scale that we're looking at in the universe? That on large scales, the classical regime is huge. These things are all totally decohered. If you look at the length scale here, 10 to the 10 meters or whatever, solar system scale, all the way down, the quantum halo is 10 to the minus, all the way down to 10 to the minus 40 metric fluctuations or something, ridiculously small. So you would need an instrument much more sensitive than LIGO or LISA, space interferometer, to detect the quantum halo, the quantum effects. But as you start going to smaller and smaller length scales, the quantum halo gets bigger and bigger, and you start getting into the quantum regime. And you also see there's an interesting bend in the curve, whereby if you go to really small scales, you're smaller than the wavelength of the particles, and the particles stop being able to notice. Finally, why do the neutrinos defeat the microwave background photons in their abilities? Because they have shorter wavelength. They have lower temperature, 2 Kelvin rather than 3 Kelvin, so you might think they have longer wavelength, but they're massive. We know now neutrinos have mass. For a photon, when you calculate the de Broglie wavelength, right, you need to look at the momentum over h bar. For a massive particle, you end up taking the square root, the geometric mean of the temperature and the rest mass times c squared, and that's smaller for the neutrinos. So this is just yet another example of how powerful Wojtek's ideas are. They can be applied to all sorts of new systems. And even if the detailed physics comes out differently, they still work. All right? Let me move on now to the main topic I want to discuss today, which is decoherence, observation, and the second law of thermodynamics. So this is based on a number of papers I've written, the oldest going back already to the 90s, not too many years after I met Wojtek, but also some much more recent stuff that I've done. And the basics, so the theme, as I said, is I think we need to it's fruitful to think about the subject separately. Richard Feynman, another one of my physics heroes, famously said that we like to divide all the degrees of freedom in nature. We like to divide our universe into two parts: the subject, the object that we're studying, and the rest, which Wojtek calls the environment. I say it's even more useful to divide it into three parts: the object we're studying, the environment, and the subject, which are my degrees of freedom that are self-aware. I don't need to know exactly how these degrees of freedom work. I can think of it as just a memory storage device that can process information. I think that if what we usually do when we teach undergrad quantum classes is we just start by having object only interacting with itself. When we let the object interact with the environment, then we get decoherence and all the interesting things that come with that: entropy increase, emergence of classicality, and so on. On the other hand, the whole business to do with the measurement problem and has to do with interactions with the subject, and I want to talk a great deal about this. This again links very much to Wojtek's own work, of course. He has for many years been talking about the environment as witness, for example, and embodied in this is the notion that to be an observer, you don't have to be necessarily conscious. There's nothing it's all about information transfer, right? And it just so happens that some systems that can process and store information also are conscious, and they behave a little bit specially, as I'll discuss. I think basically consciousness is the way information feels when it's being processed in certain complex ways, which neuroscientists may one day understand better. All we need to know as physicists is I don't think there's any secret sauce. I think I am my electrons and quarks. And that means that all of my electrons and quarks obey the same laws of the same Schrödinger equation as all the other ones. And it's very interesting so if we think about these three systems, the environment is basically the thing we always trace out. if we can think of this as something we ignore and don't know about, or we can learn about the object through quantum Darwinism by studying it. The subject, on the other hand, is a system which by definition is always in a pure state, because by definition my degrees of freedom are self-aware. Right? So if you put me in a superposition of two different states, then each one of them is going to feel that this is what happens, and they know themselves. So crudely speaking, you always trace over this system, the environment, and you always condition on the subject. And we'll come back to some equations for what that means. But why should you care about all this stuff? Isn't it just a bunch of blah, blah, blah? Well, actually, there's been a lot of interest for a very long time in the cosmological entropy problem. Why is the entropy so low? And if people just say, well, it's so low because it was even lower in the past, that doesn't tend to make the questioners stop asking questions, right? And inflation was widely hailed as supposed to help with this, but then a lot of people like Sean Carroll have claimed that it doesn't solve the problem. And then, of course, the quantum measurement problem has been with us for as long as quantum mechanics have. And I feel that all of these three are very tightly linked and ultimately have the same solution, which I want to talk more about. So just a very, very brief recap. You all know what entropy is. Of course, Shannon said that entropy is just a measure of our ignorance. That's in classical physics. So if you're ignorant about which of the what kind of playing card this is, but there are 8 options, it's a king or a queen, you would say that entropy is 3 bits. If I now tell you that, oh, it's a queen, then there are only 4 options, so I'm down to 2 bits. If I tell you it's black, I'm down to 1 bit. If I tell you that it's in fact this card, then it's 0 bits. That's classical entropy. And then von Neumann, of course, showed how we can generalize this to quantum mechanics by taking minus trace rho log rho of the density matrix, which is another way of just saying it's the Shannon entropy of the eigenvalues of the of the density matrix. In other words, instead of being asking for the classical entropy of my ignorance about that playing card, it's my ignorance about which quantum state I'm in that this measures. And as Wojtek likes to say, if you start with a totally mixed density matrix, that means something is here and, pure state, like the one in the top here, that means something is here and there at the same time. If you get rid of the off-diagonal elements, it's here or there, and I just don't know which, I've transformed the quantum uncertainty into classical uncertainty. Decoherence can transform and into or in that sense. Continuing our quick, very quick sort of recap here. Wojtek and the decoherence pioneers, of course, have shown how tracing over the environment while you're interacting with it can tend to do precisely this kind of thing where I think I had it backwards there, where you go to more mixed states. Okay, so that's entropy. So what's the deal? Why are people fussing so much in cosmology about this? How did things all start out? As we heard so nicely explained by Charles Bennett, we are in an out of equilibrium system. We're on a 300 Kelvin planet, taking heat from a 6,000 Kelvin star, dumping it into a 3 Kelvin space. That's why we evolved. That's why we can have this celebration today. And how did it get that way? Somehow because our entropy seems to have been even lower in the past. And it was that way because it was still lower in the past and still lower before then. So why did it start out in such a low state? I think, just to give you a summary in advance of what I'm going to say, I think basically the entropy of something increases. The entropy of something increases when you're not looking at it, so it's interacting with the environment, and it decreases when you do look at it. So in terms of this decomposition into the universe into 3 parts, right, when the object is interacting with the environment, as far as I'm concerned, its entropy goes up. If I put my notes for my talk in a certain place, And then while I'm not looking, my son Alexander comes and messes with it. Its entropy has increased. Whereas when instead this object interacts with a subject, its entropy goes down. I look at the playing card, oh, it's a queen of spades, entropy goes down. So you have these two processes going in opposite direction. I always find it a little odd that we are so obsessed about the second law, treating it as some kind of holy religious thing that the entropy has to go up. It's so obvious that there must be some equally important process which brings it down, since we're seeing it not anywhere near its maximum state. But for some reason, it's a little bit less fashionable to talk about that. I want to show you some formulas quantifying that, and then show you something I was very surprised actually to discover, that you might think that by just observing something and recording 3 bits of information about it, all you can ever do is reduce its entropy by 3 bits. In which case, the mechanism I'm proposing would be utterly incapable of explaining the low entropy of our universe, right? There's no way I can bring the entropy of our universe down from over a Google, to 20 orders of magnitude lower, 10 to 20 bits lower, by just observing it, if I can't store 10 to 20 bits in my head, right? But I'm going to tell you about a very interesting mechanism whereby, by observing just a few bits, you can actually bring the entropy of our universe down by enormous amounts. Okay, and this is linked a little bit also to Wojtek's work on phase transitions.
Can I slow you down a little bit?
Yes.
Clarification. If I were to look into the room in which your son Alex messed up your books,
Yes.
would the entropy decrease for you as well?
You're just looking at it, not messing with it any further.
Yeah.
No. So
Entropy is a personal thing. That's what I'm getting at.
I'm very glad you asked. So let me make my definitions clear, since everybody's entitled to have the ones that are different from mine. I'm talking about the density matrix, and to me, the density matrix is simply the super useful tool that helps me predict everything I can possibly predict about the future, about my future. Okay, and so my density matrix is actually different from yours. If you've looked, you'll use a different density matrix than I. Even if the universe as a whole has a single unique density matrix, which might be a pure state, each and every one of us in the room has a different one, all right? Thank you so much for that. So Seth Lloyd gave a very, very nice definition of the second law of thermodynamics in his PhD thesis from 1988, where he pointed out that even if you have an isolated system where the entropy is 0 and will always remain 0 in terms of this omniscient, fictitious observer who knows everything, right? If you don't know exactly what the dynamics of the system is going to be, then you will always find that the entropy increases. So Seth is one of the many colleagues of mine who view entropy as a measure of our ignorance about the quantum state. But not everybody agrees with Seth and me about that. For example, the famous philosopher...
This was pointed out classically by Borel in like
It was, but Gibbs and Boltzmann used to argue about this, whether it was really something to do with what we know about a system or not. And as recently as this recent conference we organized in Copenhagen, famous philosopher David Albert, who many of you know, said that thinking that entropy has anything to do with what we know about a system is a bad, misleading mistake. So I just want to alert you to the fact that I'm presenting a particular view, and not everybody agrees with it. I disagree with David Albert. I feel, as I was just saying in response to Wojtek's question, that I'm interested in using physics to make predictions about my future. In fact, I believe that's the reason that I evolved the brain in the first place. And knowing the full quantum state of the whole multiverse not only is not enough to do that, but it's also not necessary. Knowing the full density matrix of the universe is not necessary. It's not enough. It's not enough because I also need to take into account what I know about my location in our universe. If I know everything about every atom in all of space, I have to know, okay, where in this business am I? to be able to predict what I'm going to see and what's going to happen next. I need to know where I am in three-dimensional space. I also need to know where I am in Hilbert space, in what branch of the wave function, to be able to predict. If I know that that all of quantum reality is a superposition of many different states, some of which have no planets at all, some etc. I need to know what branch I'm on. Now, it's also not necessary for me to know all of that stuff, because I only need to know my quantum state nearby, metaphorically speaking. Nearby in three-dimensional space, it's quite safe for me to trace out what's outside of our cosmic horizon. I actually can safely trace out what's outside of our solar system to predict what's going to happen for the next few hours, just because of causality. I also only need to know about what happens nearby in Hilbert space. So to make this a little more clear, the standard picture of cosmology, if you have unitary evolution, says we start out in some quantum state of some sort, okay? Then we have inflation. We have all these quantum fluctuations. And even though many of my astro colleagues who aren't as interested as you in quantum information then wave their hand and say, oh, at some point these go classical. And they'll say, oh, well, then there's some guy, Zurich, who explains why. The fact, of course, is that we have this quantum superposition of all these different things. They all decohere. So what we end up getting is a superposition of many different classical-looking universes where the galaxies are in different places in each branch. Right? And there are also some branches symbolized by the skull up there where you probably fail to get any galaxies at all. And I don't care. If I just want to predict what we're going to have for dinner tonight or something about my future, I don't need to care about those other branches because they're so firmly decoherent from us that I don't need to know about them. I just need to observe, okay, I'm in this particular solar system with 8 planets and ta-da. I can ignore the rest. So to summarize, to go from the full density matrix of everything to the one that I actually need to use, there are 2 separate processes I have to do. First, I have to condition on what I know. I'm the subject. I know there are 8 planets. I know I'm in Waterloo right now, so I can disregard all possibilities which are inconsistent with that. And second, I need to partial trace over all the stuff that are irrelevant to my predictions, to keep the calculations manageable. Okay?
There's a good term that Peter Thiel coined, dynamical independence.
Dynamical independence.
Yeah, once a branch is decoherent from your branch, its dynamics doesn't influence you, and your dynamics cannot touch it.
Beautiful. So beautiful. So anything that's dynamically independent from me, we don't care about. And part of the reason we evolved the brain was, part of the reason it's useful has to do with that, of course. 'Cause if we had to keep track of too much information, more bits than we can store in our brain to predict anything, we wouldn't have brains. So let's just very briefly look at the different kinds of interactions between these systems. So you can take any Hamiltonian and you can write it as as a sum of different parts. A part which applies only to the object, the part that applies only to the environment, the part that applies only to the subject, as a part which couples the object to the environment, which Wojtek has studied an enormous amount. There's also a part that couples the object to the subject. And then there's a part that couples the subject directly to the environment. And you can have a part that in principle couples all 3. And these different parts have very different effects, right? The object-environment coupling leads to the object decoherence. The entropy of my object increases because of this. This term here, coupling me to the object, is responsible for measurement, observation, the apparent wave function collapse. It decreases entropy. Direct decoherence of the subject can also be interesting. I'm not going to talk about it today, but for example, whenever a neuron fires or not fires in a superposition, that decoheres in like 10 to the minus 20 seconds or so. So it's very hard to have, it's very natural that your consciousness feels kind of classical. The unitary evolution, for example, you can take something which is in a fairly well-defined position. If you balance a card exactly on its tip and you have a Gedanken experiment where there's no air, no perturbations, it's perfectly sharp at the bottom edge, it will still fall down into a superposition of left and right in less than 30 seconds. It's a classical grad student homework problem, right? That's unitary evolution, producing Schrodinger cat-like states. Decoherence, I drew this picture very much inspired by a paper you wrote once in Physics Today, Wojtek. And if you look at the Wigner function, actually this is a density matrix, sorry, how interacting with the environment suppresses off-diagonal elements. And then when you observe, suppose I bet money, I bet $100 with Seth Lloyd that the card is going to fall down face up. Then if it falls down face up, I get happy, and if it falls face down, I get sad. And so my electrons, my state gets entangled with the state of the card. There will be two versions of me in the final wave function. Both of us will know what the state of the card is in our branch. So if you look at it like this, I have my eyes closed. There's no entanglement between me and the system. I know the state though, so I would just say the system has 0 bits of entropy. Now it's fallen down, my eyes are still closed, so I would say it's 1 bit of entropy for the card after if it's decohered. And then I look, now I'm entangled with it. There are two versions of me, but 0 entropy for both of us. So if you draw this like a cartoon in this way, this is the traditional splitting of worlds that you, Everett, talked about and Chuck Bennett also mentioned. If you look at this in terms of the density matrix, if there are 2 states for the card, 3 states for me, when with the index changing fastest is the one of the card here. I have my eyes closed. The card evolves into superposition of up and down. So I have these off-diagonal elements. Decoherence kills that. Then I interact with the object, so I get entangled with it. Now the density matrix looks like that. This density matrix I can now write as a sum of 2, as an average of 2 perfectly good density matrices, right? One where I'm happy because I won $100, card is face up. One where I'm sad, card fell down. And since we're assuming that the subject is by definition always in a pure state, there will be 2 maxes effectively, and this is what the density matrix, the first one will use. This is what the second one will use. So what counts as an observer? We can, as Wojtek and others have emphasized, it doesn't have to be a human being, really. To do these calculations, you really just need to have an information storage device of some sort. Photons, as we heard about a lot already earlier today from Charles, are perfectly good at storing a lot of interesting information. If you have a mirror which is either at position A or position B and you bounce one photon off of it, the position of the photon will know where the mirror was. Just as I said earlier, the position of the photon that's traveled through this room will know whether there's a black hole in here or not, because that will affect its position. So let's look a little bit more quantitatively at this, okay? The first kind of effect, object-object interactions, keeps the reduced density matrix of the object just evolving along with constant entropy. That's quantum 101. When the object interacts with the environment, you get decoherence, entropy will increase. And if we go back to the Old Testament again, Dieter Che, Wojtek Zurek, and so on, very simple, nice way to model this is you start out with the object. The object it can be in various states. They have some basis O sub I, or the different object states. And we have an interaction which keeps that unchanged. But it changes the state of the environment depending on what the object is. So the environment starts out in some initial state, and eventually, but afterwards, these epsilon i's depend on what the object is. And the opposite, we'll come back and talk more about that. That's the most general kind of decoherence. The most general kind of observation, you can have very weak decoherence, of course, where the environment learns almost nothing about the subject. Or you can have very powerful decoherence where all the off-diagonal elements go away. It's the same with observation. The classical observation that we learned about in from the definers of quantum mechanics, assume that you got complete information in some sense. But you can define analogously a process like this, where I start out with the observer in some state O sub I. It's the same exact math as for the environment. I just changed the letter. I just changed the letter E for environment to S for observer, and epsilon for environment, Greek environment to epsilon for the sigma for. Sorry, I changed E for environment to S for subject. And my phone keeps ringing, but now it's not. And this formula here, which I'll tell you more about in a moment, I think of it as the quantum mechanical version of Bayes' theorem. I talked about how I just love robocalls. Okay. I talked about how when you go from the full density matrix of everything to what we care about, you trace out the environment, and you condition on what you already know. Bayes' theorem is the classical statistical way of doing that. I have some probability distribution, and then I take the conditional probabilities given what I know and update my prior probability into my posterior probability, right? This formula here does exactly the same thing, but now for the density matrix. I have a density matrix, and then I interact for my object. I interact with it in some general way. I condition on what I learned, and now that gives me an updated density matrix. If it's a complete measurement, that will always put my object into a pure state. But if it's a weak measurement, it won't. Quite generally, though, you would expect that it will always decrease the information, or at least that it will on average decrease it. And I'll show you proof of that in a moment. So how can one make this a bit more rigorous? So in words, we would expect then that you can take the second law and you can say, split into two pieces. You can say that the entropy of the object cannot decrease unless it interacts with a subject. So I'm not looking at it, but then the standard second law says it can't go down. Moreover, the object's entropy cannot increase unless it interacts with the environment, if you know what the evolution is. Otherwise, you get Seth-Loy's theorem. So let's look at the second one first, the business about how decoherence increases entropy. So if we go back to this standard derivation that Wojtek and the decoherence pioneers did, what actually happens to the reduced density matrix is it just gets multiplied by the components of the density matrix get multiplied by this other matrix I've called capital E here, which is all these dot products of the environment states. The way you can write this with the smallest number of symbols involves this circle, which after studying the math literature I learned is called the Schur product. So the Schur product of two matrices is different from the ordinary product. You just take the two matrices and you slap them on top of each other and you multiply each element with the one that's lying on top of. It's that kind of multiplication that happens to the density matrix, okay? And we clearly expect that if you take the Schur product of the density matrix with any decoherence thingy like this, which is a matrix which can't have negative eigenvalues, right? And its diagonal elements have to be 1. So it's a correlation matrix, basically, or a complex valued version of it. You would expect that the entropy should always increase unless there's no decoherence at all and the environment didn't learn anything. And it's easy to prove that for some simple cases. If you use linear entropy, Renyi entropy, it's easy to prove. And if it's a perfect decoherence, so the thing goes diagonal, that's easy to prove too. But maybe you know it, but I couldn't anywhere in the literature find a proof of this most general claim. Even though it's super easy to just write down the claim, the entropy of the decohered or the partially decohered density matrix, the Shannon entropy, should be bigger or equal to the original one. So in a paper I wrote some years ago, I actually put in an exact proof of this, and I'll just share it with you now because I think it's a very useful result. If you know of it in some place in the literature that I don't, I would appreciate if you tell me. Maybe you could tell me afterwards. I didn't find it in or do you want to shout out?
No, there's a name for this type of matrix
matrix that's built out of inner products of...
It's called a Gramian.
Yeah, there you go.
Exactly. I didn't want to bombard you with too much math jargon, but exactly, a Gramian matrix. So the claim is to take any positive definite matrix of trace 1, sure multiply with a Gramian, the Shannon entropy goes up, unless the Gramian is just all ones. And so the proof is actually quite simple. Well, most proofs are simple after you've figured them out. But there was a beautiful theorem in 1980 proven by mathematicians in 1985. Okay, Bapat and Sunder studied some stuff with Schur products, and they showed if you take their theorem and then you do a little bit more work, you can see that implies that the eigenvalues of the density matrix majorize the eigenvalues of the decohered, partially decohered density matrix. Raise your hand if you know what majorization means. I see almost everybody, so I won't dwell on it in particular. It basically, if you have a sequence of numbers that add up to 1, probabilities, one such thing majorizes the other if the first guy here is bigger than the second guy, and then the sum of the first two beats out the sum of the second two, and so on. And it's not too hard to see that if you make what I like to call a Robin Hood transformation of your probabilities, where you take from the rich and you give to the poor. So, in other words, you're like, if you take some probability away from the big probability and give it to a smaller one, okay, that will always give you a case. That will always mean that the former majorizes the latter. And that's also exactly the kind of thing which increases entropy. Right? You're smearing out the probabilities, making them more equal. And it's also easy to see that whenever this is something I think you already generally all know, that if the spectrum, if the eigenvalues of a density matrix majorizes those of another, that means that the second one will have a higher entropy. And it's more general than that. If you have, for any sum of a concave function of these probabilities, the sum will be bigger in the decoherent version than in the non-decoherent version. So if you choose the concave function to be minus p log p for the entropy, then that immediately proves this, that decoherence always, if you take two, as long as you're not entangled with the environment to start with, you're guaranteed to increase the Shannon entropy. If you instead pick 1 minus p to the alpha, where alpha is positive, that's also concave. That proves now that the Renyi entropy also increases for any alpha. If you pick log p to be your concave function, that proves that the determinant of the density matrix always increases, because the determinant is the product of the eigenvalues, but the log of the determinant is just the sum of the log of the eigenvalues, right? So in one fell swoop, this is a beautiful, this Bapat-Sunder result is very nice. And it came kind of late in the game. It came only in 1985. So I don't know if, but I think this is it's a very easy result to remember. You had a comment here.
Yeah, I mean, I guess what you're calling the Shannon entropy, I assume is what I would call the von Neumann entropy.
Sorry, I misspoke. I meant the von Neumann entropy, yeah. The whole time when I said Shannon.
And I was also going to mention this, if the initial state is entangled, then you can, of course, decrease the entropy.
Exactly right. So the only assumption that goes into this theorem is that initially the two states are initially the environment and the object can be factorized. Then this happens. Now, so that's this. So that I put in that first paper. But then, what about the other part? You would think that when you observe something, it would be nice to prove some kind of theorem saying that you're guaranteed to learn something by observing. It feels very intuitive. Okay. Now this turned out to be much harder than I thought. Classically, Shannon already nailed this, because Shannon pointed out that if you observe something and you use Bayes' theorem to update your probability distribution for what's going on, so most of the time the entropy will go down of the thing you look at, but not always. You can cook up situations where the entropy will go up, but on average, Shannon showed it always goes down. How much does it go down by on average? Exactly by the mutual information between you and the other thing. Beautiful result by Shannon. And Shannon, of course, also showed that the mutual information can never be negative. So in other words, you take yourself, you go observe a system that was initially not entangled or correlated with you. On average, Shannon says you will learn something. How much do you learn? On average, the same number of bits as the mutual information that resulted from the interaction. So first I thought, maybe I can prove the same thing for quantum mechanics. But then I realized, no, that's of course impossible. Suppose I have just one bit, a spin-1/2 system. No? The mutual information between me and it, if we're in a Bell pair state, can be 2 bits. There's no way I can reduce the entropy of a 1-bit system by 2 bits. Then it would have an entropy of -1 bit. So it can't be quite as easy as just carrying over Shannon. But I thought, but it's got to be true. And I started running all these numerical simulations. I tried tens of thousands of numerical examples to look for counterexamples. It always worked. So at this point, I was a believer that this must be true. But I couldn't prove it. And then something really fun happened. So this is the theorem just in math terms. You just take this quantum Bayes theorem and ask, on average, how many bits does the entropy go down when I look at something? Okay. This undergrad student, Hrant, from Armenia, a super awesome guy, came to me and said, hey, I wonder if you have a little project for me at MIT. I have to do a project for my quantum course. And this guy, I normally would not give a hard problem like this to an undergrad, but he just struck me as just extremely talented. He's the kind of, he won the physics Olympiad and gold medal and all sorts of stuff. And I thought, even if he can't solve this problem, he'll learn a lot of cool stuff about quantum information. So I said, why don't you, here is a very clear problem. Can you prove this? And he went away, and it was really hard. He started devouring all the literature on Schur majorization and a lot of very abstract math. And it was kind of like, pulling teeth, working on this. Here he is pulling his teeth out. I should tell you for truth in advertising that he didn't pull his teeth out for this quantum project, but because of a rendition of the play Electra that they did the other month. But one day, he came to my office, and instead he looked like this. And I knew he had solved it. He had found the proof. And he found this beautiful proof where you go back and it doesn't follow even from any corollaries of the Bapat-Sunder theorem. But you take sort of the same general machinery and you use it in a different way. And I'm not going to bore you with the mathematical details, but it's a beautiful proof. And the result is, again, super easy to remember. The result is simply that if you observe an arbitrary quantum system that you were initially totally uncorrelated and independent from, on average, you learn something. Just like in classical mechanics, classical physics with Shannon, but not necessarily as much. Okay? So that was fun. And I have about 6 minutes left, right? So in my last 6 minutes, let's connect back a little bit with cosmology. So I motivated all of this stuff by saying, I would like to understand why our universe seems to be in such a low entropy state. Its entropy is, by even a very conservative count, 10 to the 20 times, 10 to the 20 bits less than you might expect it to be, or 10 to the 30 bits less. I don't know about you guys, maybe you have better memory than I do. I have a hard time remembering phone numbers with, let alone 10 to the 20 bits in my head, which can't be stored there. So if it's true that this process of lowering entropy by observing can only lower the entropy of the environment by the same number of bits that you've measured, that cannot be the explanation for why our universe seems to have such a low entropy. But then I realized something that I thought was very interesting, which is if you unify the two sides of Wojtek-Zurek, you can decrease entropy by a lot. Okay? You put together these ideas from quantum mechanics that we've discussed with an idea from cosmology. You can do it with inflation, in particular, which is a process which creates very, very long-range quantum correlations. It turns out you can also do it with phase transitions, which Wojtek has been working very hard on recently. And interestingly also, Seth Lloyd recently came up with this very interesting idea of replacing inflation as an explanation of why we have these density fluctuations that gave galaxies by a phase transition. So if you do that, turns out you'll still solve this problem, the entropy problem too, even if you weren't aware of that success. You can chalk up. So what am I talking about? Let's look at a very simple toy model. Suppose we have a universe where, we'll just divide it into little squares so I can plot it, okay? And each region here can be either inhabitable, green, or uninhabitable, red, okay? And there's some process which creates these big regions that are contiguously habitable, but it doesn't percolate to all of space. This could be inflation having happened and made some regions very nice and uniform, whereas the red ones might be full of microscopic black holes and all kind of nasty stuff. Or maybe it's some phase transition where you have these large regions which are percolated out to some horizon scale or whatever. Doesn't really matter. We'll start with a quantum state, which is the superposition of all possible things like this. And then we go and observe. If we start looking at the one little voxel that we're in, measure whether it's red or green, we get one bit of information. Then we observe as maybe the little piece of space, one Planck volume over, or whatever, the next voxel, and then the next. We keep measuring more and more bits. And every time we do this, we apply the quantum Bayes theorem that I showed you to update our density matrix. And we recalculate the entropy that we ascribe to everything, okay? And we see what happens. Now, what happens is actually very interesting. It turns out that if there were not for this effect, the inflation or the phase transition, which caused the long-range entanglement, if you just started with a totally random soup of stuff in thermal equilibrium, then the entropy of the rest of the universe is a function of how many bits you've observed, goes down linearly, just like you would expect. You measure 1 million bits, the entropy goes down by 1 million bits. But if you instead have this inflationary or phase transition state where you have this long-range entanglement, this is the formula I derived for the entropy of the rest as a function of how many bits I've observed. And look, it falls off exponentially with the number of bits. It goes down like, the leading term here has a 2 to the number of bits downstairs. So at the limit of observing lots of bits, every bit I do, I cut the entropy in half. I plotted only a small example here going up to 50, so it would show on the scale, but you could take this going up to 10 to the 100 bits, or 10 to the 123 bits, or whatever. And then every time you measure one bit, you get to cut that in half. And you don't need to take 10 to the 100 and cut it in half all that many times to reduce it by 20 orders of magnitude, right? You measure less than 100 bits is going to do it. So this means that actually, if you just combine this basic idea that the entropy can go up and it can go down, it can go up, it generally goes up when we're not paying attention to things, but it will go down when we look at things. If you combine that with some mechanism that happened, preferably before we came on the scene, which causes long-range entanglement, inflation or phase transitions or something else, then in fact, you will bring the entropy down enormously of your environment by just being self-aware and observing a little bit. And I think this actually provides a very natural explanation for why our universe is so orderly and in such a low entropy state, and for why ultimately we're able to have this conference. Which brings me to the very last thing that I want to say, which is it's really fun to be here, and I want to wish you, Wojtek, a very belated and very, very happy birthday. Thank you, Wojtek.